Good morning, folks. Welcome back to quantum mechanics once again. Last time we talked about a topic that sometimes is perceived as tricky, which is spin-orbit coupling. It sounds kind of spacey, and therefore people feel like, wow, I have no idea what that means, but hopefully, last lecture made clear that it is simply the fact that the electron has two sources of angular momenta, and they can either reinforce one another or suppress one another, right? So we can have combinations in which the angular momenta of the electron add up and situations where they basically subtract, and therefore the electron has an effective low angular momentum. The angular momentum does play a role in the energies of the states that the electron can sit in, and that led to what we call spin-orbit coupling splitting. Okay, and so we saw an example last time in the hydrogen atom, and today I'd like to basically continue that story and make it hopefully a little bit more concrete, so hopefully how to think about this problem. So here on this slide, you can see the energy level diagram of the hydrogen atom. Okay, so we see here the states, the quantum mechanical states that we have identified. You see the main quantum number, the principal quantum number n, and the lowest state is a wave function. All these little lines are corresponding to wave functions with a certain energy. The lowest one is psi 1, 0, 0. 1, of course, is the principal quantum number. The first 0 is L, the angular momentum quantum number, and then ML equals 0 as well. That is the 1s state. But remember, every time you see such a diagram, every line represents an actual wave function, the wave functions that we have found by solving the Schrödinger equation. That hasn't changed. It's still the same thing. But today we're going to focus not so much on the shape and the properties of the wave functions, but really on their energies. Okay, so you see here all the way on the left, a couple of numbers. Those are the energies of the respective states. And let me just make that more explicit. The energy of the hydrogen wave function is the following formula. It's H times C times RH. And this is the same as we saw last time. I'm just writing it slightly differently in terms of a new constant, RH. What is the RH? Well, that's basically a whole bunch of constants that we previously found. We put them together and we give it a different name. Okay, RH stands for the Rydberg constant. The Rydberg constant. Okay, so here it is. It depends on the reduced mass, which is the combination, of course, of the electron mass and the mass of the proton in the hydrogen atom. Then e to the power fourth, that is the electron charge to the power fourth, and then divided by 8 epsilon naught squared, that is the vacuum permittivity, times h to the power 3, and then the speed of light. Okay, so that is called the Rydberg constant. It's an important constant, as you will see hopefully in 2 seconds. So let's again look at this formula for the energy. We see that it is scaling with the Rydberg constant times hc. So h times c times RH is called the ionization energy. Okay, that has a number. It's 2.180 times 10 to the minus 18 joules. Okay, so that's an energy. And what does that energy mean? Well, it has a name. The name is ionization energy. So that has probably something to do with the fact that if you eject the electron from the hydrogen atom, that is the energy that you would need. Okay, so you need a total of 2.18 times 10 to the minus 18 joule to accomplish that, to take the electron out from the atom. So let's focus on that for a couple of seconds. As you can notice, as you can see, the energies here, all the way on the left, I'm circling them now, have negative signs. The negative sign is important because that means that the electron is bound. When the electron is bound to the atom, so it has basically an interaction with the proton. So it's bound to the proton. It will stay there. It will not fly away. That is an indication that it's bound, and that is a negative energy. So binding energies are having negative values. And you can see as n is increasing, that this value becomes less negative. Okay, this whole number becomes smaller, so it becomes less negative. And here, for n equals infinity, this level here, we basically find E equals 0, meaning there is no binding energy anymore. The electron is no longer kept as part of the atom. So whenever n equals infinity, which is of course a little bit of an abstract notion, but basically saying when n goes up very, very high, I'm approaching E equals 0, and that means that the electron is no longer bound. That's the moment when the electron will fly off, if you wish. So what is the energy then that is needed to go from all the way here, if the electron sits in a ground state, to all the way up there, okay? That is the energy, that's the ionization energy. And that is, of course, a difference between the first state here, all the way down, and the state that corresponds to E equals 0. All right, and that, of course, is if you put in here infinity, you get 0. If you put in 1, you get H times C times RH, which is this number right here. So effectively, this number is the energy that you need to kick the electron out of the atom. That's the ionization energy. And again, the beauty here is that we can just compute that number, not necessarily from experiments, but from this bunch of constants over here. All right. So again, it's a wonderful affirmation of the power of quantum mechanics, because it predicts, based on a whole bunch of constants, natural constants, physical constants, what is the energy that you would need to kick the electron out of the atom. And that corresponds very closely to what people have found experimentally. Actually, it's really, really a really good prediction. So that is the ionization energy. Okay, so let's look at the splitting now because of the spin-orbit coupling. That was a topic on Monday. Okay, so what we do here, we focus on the level n equals 2, the p orbital. So we now imagine that our electron sits in this state. But as we noticed, this state is not just one state. First of all, there are 3 p states always. And there's 2 ways in which the electron can sit in those p states, up and down, spin up and spin down, which is a total of 6 possibilities. As we saw last time, those 6 possibilities actually are not just all the same. They're in fact split into 2 ways. 2 ways. One, the upper one has 4 different ways of doing it, and the lower one here has 2 ways of doing it. So it's still a total of 6 ways to arrange the electron, okay, in this state, but there's a splitting between possibilities. The upper one is 4-fold degenerate, the lower one is 2-fold degenerate. They have names now. You put this capital P here, that's a term symbol. This one here is the total angular momentum, J, that's the number J, and this one is the spin multiplicity. Okay, and it says 2 here. Remember, this is 2s plus 1. That means that s is half. So every time you see a 2, you're dealing with 1 electron. Okay, so this is in a 1 electron state. This 2 means it's a 1 electron state, meaning there's 2 possibilities to arrange spin. If you have 1 electron, there's 2 ways to do that. That's what the 2 really stands for. The capital P stands for the total angular momentum due to orbital angular momentum of the electron. And because it's in a p state, it gets here a capital P as well in the case of 1 electron. So that's what we talked about last time. We also said a little bit about what is the energy difference here between these 2 states, these 2 spin-orbit coupling states that now split. Okay, split because they have different J values. So we said something about it, we didn't really make it very explicit, so let's do that now. Let's calculate explicitly what is the energy between these 2 split states. And in order to do that, what we want to know is the energy difference. Now we're going to compare this energy difference between the energy difference between the so-called unsplit states, if you want, between n equals 1 and n equals 2. So this transition here from an electron from the ground state to the n equals 2 state, that is something we're going to compute first to get a number and then compare this splitting energy to it. The outcome is that this splitting energy due to spin-orbit coupling and hydrogen is very tiny compared to the transition energy from the electron in the ground state to the n equals 2 state. So these two numbers we're going to compare to one another. So let's start with the delta E due to kicking an electron from n equals 1 to n equals 2. We can do that. We just have to subtract the energies from one another. The energies are given already here. Okay, so this is the energy of the n equals 1 state. That is the energy between the energy of the n equal 2 state. We just subtract them from one another to get the delta E, and that's given right here. We can fill out the numbers because now we have an expression for whatever H times C times RH is. This number, remember from the previous slide, is 2.18 times 10 to the minus 18. This is an very easy computation to do, just 1 over 4 minus 1, and the answer is going to be 1.635 times 10 to the minus 18 joule. Okay, so that is the energy difference between n equals 1 and n equals 2. This is a good number to keep in mind. Okay, sometimes you see those numbers, you're like, well, it's 10 to the minus 18, it's a very tiny number, don't have to think about it as much, but it's very helpful if you have this number kind of somewhere in your registers, okay, because 10 to the minus 18 is a typical energy that is needed to kick an electron from one state to another state in an atom. Okay, so these are the magnitudes of the energies, the transition energies in atoms between typically a ground state and a first excited state. So if you are asked to compute such energies, transition energies in atoms, and you find numbers that are much smaller or much higher than this, then maybe something is off, right? It should be on the order of 10 to the minus 18, 10 to the minus 19, sometimes 10 to the minus 20. But if you find something that is on the order of 10 to the minus 4 joules, then you did something wrong in the calculation. So keep that in mind. Having a sense of the magnitude of numbers is really helpful to analyze a problem. Okay, so now we have that number, 10 to the minus 18 about. Let's compare that with the splitting energy due to spin-orbit coupling. Okay, that's the next thing we're going to do. And in order to do that, we will take back the formula from last time. This is the formula here that we derived last time in the lecture on Monday. This is the splitting energy of a particular state due to spin-orbit coupling. Okay, so this is the spin-orbit coupling energy. It has a prefactor with this A tilde, and that is the spin-orbit coupling constant, which is different for each atom and also for each electron in the atom. Okay, so we will not specify this, even though I have provided a formula for this in the lecture notes, which are posted online, so you can have a look. But the most important thing that we should know is that this A scales with z to the power 4. Okay, what does that mean? That means z, of course, is the charge of the nucleus of the atom that we're looking at. If it is hydrogen, z is going to be 1. Okay, so that's a small number. But if you go to other atoms, of course, the z to the power 4 is going to blow up really fast. In other words, the coupling energies due to spin-orbit coupling are very tiny in hydrogen, but they can be very big for other atoms, especially for heavy atoms, heavy elements. Okay, so and we'll see that in a few moments. But for now, let's take this formula and compute what is the energy of that state and the energy of this state, right? These two states, these are the spin-orbit coupled states, or the split states, and then compute the difference between them. Okay, so this is what we're going to do. So the splitting energy of the first level, that is the 3/2 level, I'm going to compute the splitting energy. So what is that splitting energy? Just to make that clear, that is the energy that is indicated here. That is the splitting, the energy that this guy gets because it is because of spin-orbit coupling. Okay, so that is these little arrows that we calculate here. That is ESO, the splitting energy due to spin-orbit coupling. So we just fill out the numbers of this state. We know that J equals 3/2. So that's the J right here. Okay, this is the J value. The L value is 1 because the electron is in a p state. Okay, so L equals 1. So I'm filling out right here. And then S is also very easy to trace back because we only have one electron and S is always half for one electron. Okay, that's the spin quantum number for one electron, which is half. So I just fill that out, and what I'm getting is plus half H times C times this A tilde, which is the spin orbit coupling constant. So that's the splitting energy of the first state, the upper state. Let's do now the second state. Okay, so tentatively, if I put it in a diagram, that is this energy right here. All right, so it should have basically from this image, I can see that this energy, the spin orbit coupling energy of the second state, is going to be a negative number. So let's see if that is true or not. Do the same thing. The main difference is only this value for J. Everything else is the same, right? The L level is the same. The spin is the same. The only thing that's different between these two states is the J value. That is this value right here, okay? Those are the J values. So fill that out, just filling out that formula. It looks scary because it's a whole bunch of numbers, but really the L and the S are just numbers. So just plug them in and compute what you get. Yes, indeed, there's a negative sign as I expected from the diagram above. It's minus H times C times this A tilde. And what I can do now is to determine the difference between these two energies. Okay, so let's do that. The energy difference is going to be half times H times C times A, and then minus 1 HCA right here. So that is delta E. That's the difference between these two states. And that is going to be 3/2 times H times C times A. Okay, so that is what that's what I'm finding. There was a question about what is this half? This half is just part of the derivation we did last time. Okay, so the spin orbit coupling energy is just this expression right here. We derived it last time. You can go back to the notes and you'll find the same expression there. So it's just implicit in the derivation. This half is just part of it. Okay, so let's, I meant half towards the end. So this half is the spin, okay? That's the spin quantum number, and the spin quantum number is always half if you have one electron, because that is the spin quantum number of an electron. That's half. You will see that this S can be having a different value if you're dealing with 2 or 3 electrons. We'll talk about that next time, not now. We only have one electron. This little s is simply the spin quantum number of an electron, which is half. Okay, so let's compute, because we have now an expression, 3/2, H times C times A tilde. A tilde we can compute as well, okay? I will not show you how to do that, but there is a remark in the lecture notes. You can see how I did that. And if you plug in the numbers, you find the following. 7 times 2,2 times 10 to the minus 24 joules. Now, this number is 10 to the minus 24. Previously, between N1 and N2, we found 10 to the minus 18. Remember that? So this energy here is about 1,000,000 times smaller than the energy difference between the state 1 and state 2. So the difference between state 1 and state 2 is enormous compared to this little tiny energy due to spin orbit coupling, right? So if you see the spectrum of hydrogen, you see lines, and we'll talk about these lines next. You see these very sharp lines. These are emission lines. The picture above are the absorption lines. Absorption means the missing of photons. The emission is the production of photons by the atom itself. Very narrow lines, but in fact, these narrow lines are split just a little bit due to spin orbit coupling. But as you will see, this energy is so tiny that it's basically very hard to observe. So this looks really like a single line. All these lines look like single lines, but in fact, if you had a magnifying glass and a very high resolution spectrometer, you will be able to see that, in fact, there's tiny little splittings. These splittings are about 1,000,000 times as small as the energy difference between these lines, or the energy difference due to the transition energy itself. Right? So there is splitting on top of this, but it's too hard to see for all intents and purposes in the case of hydrogen. You'll see that it's not true for other atoms that are heavy elements. So before we introduce some heavy elements examples, I want to say a few words about, how to think about these lines, these transition energies. Because what really governs that? What determines what kind of transition an electron can make between states? Are there limitations? Can the electron go to any state, or are there restrictions on to which state the electron can go due to the absorption or emission of a photon? Okay, I have to stress that, because we're looking specifically at transitions that are mediated by photons, not transitions that are mediated by something else. For instance, heat. Okay, heat is also a form of energy, and there's different rules for heat than there are for the use of photons to enable transitions. So let's look at transitions between states due to the involvement of photons, aka electromagnetic fields, right? Because a photon is a form of electromagnetic radiation, quantized electromagnetic radiation. Here is what we will do. What the photon will do is the following in the atom. It will couple to the charges of the atom. Okay, the atom has, of course, charges. The nucleus is charged, the electrons are charged, and since the photon is electromagnetic radiation, electromagnetic field, it will move those charges along. Now, this dipole here is going to tell me, this mu means dipole, will tell me how successful the radiation was in moving the charges. Because if the electric field that the photon is moving the charge by a value r away from its equilibrium position, it basically has generated a little dipole, which is proportional to the distance r, how far the electron has been moved by the field, times the magnitude of the electron charge. Okay, so what we're looking at here is the movement enabled by the presence of the photon that has moved the charge a little bit away from its equilibrium position. And that created a dipole, an induced dipole, a dipole induced by the presence of the photon, by the presence of light. Now remember, I'm only talking here about E, and that is because I'm only considering the electron charge. I'm not considering what the light is doing to the proton. It turns out that in many cases, at least for the radiation that we're interested in here, which is visible radiation, it doesn't do much to the proton, okay? It doesn't do much to the proton. It mostly interacts with the electron. So that's what we will be focusing on. We'll focus here on electronic transitions. But there are also transitions that are not electronic in nature, but actually coupled to the protons directly. That is infrared radiation. Okay, so the same principles apply, but for all intents and purposes, we will focus only on the displacement of the electrons due to the fact that the light is there. Now, quantum mechanically, the dipole that I'm inducing in my proton, or sorry, in my atom, in my hydrogen atom in this case, is written in exactly the same way, but now I have little hats here because these are operators, right? They're not just quantities, they are actually operators. So this is an electric dipole operator, and it's proportional to the electron charge times r, the position operator, where the position operator now indicates the movement away from the equilibrium position that the electron had. So the following is a very important statement in quantum mechanics that says that transitions are, of course, mediated by the shaking of charges, and that the magnitude of that is described by the following transition dipole moment. Okay, so what I have here is an integral, and the magnitude of the integral is summarized by this symbol right here. It says mu IF, where I indicates the initial state in which the electron sat, and F is the final state in which the electron sits after it has interacted with light. And this is what the integral is. Okay, so here we see the dipole operator. This is the dipole operator. It basically tells me how successful is the light in shaking the charges, in doing something, and moving the charges in my atom. If the light can't do it, then not much will happen. But if light can do it, if it's able to cause a displacement of the charges in my atom, then this dipole operator is a non-zero thing, right? Now it's sandwiched between two wave functions here, as you can see. The first one here is I, that is the initial state, the complex conjugate of the initial state, and then the second one is F, that is the final state. Okay, so the dipole operator is sandwiched between the states I and F, and then integrated over the entirety of space. Now, there's a way to summarize this in our kind of infamous bra-ket notation. We just say the state I, and then the state F, and the dipole operator is sandwiched between these two states. This integral here, if this integral is non-zero, that means that the shaking of charges has led to the movement of the electron from one quantum mechanical state to another quantum mechanical state. So whenever this integral here that you can see is non-zero, that means that you have actually enabled a transition between two states due to the fact that the charges responded to the presence of light. Okay, so it basically translates what is happening during a transition. What you need is you need light that is shaking the electrons enough such that you move from one state to another state. You perturb the system enough such that the system says, forget about it. I will no longer be in I will now be in F, right? But you have to be able to communicate with the atom first, and that happens by moving the electron away from its original position and moving it towards a position that is more reminiscent of the position of the electron it would have when it was in F. Okay, so the light is basically causing that. It's causing a transition between quantum mechanical states. It's moving it away from the original state and placing it into a state that is reminiscent of the final state, and therefore it will now be in a final state. So quantum mechanically speaking, the transition is going to be successful or allowed if the integral you see here is non-zero. Okay, so that's basically what I'm trying to state here. I'm saying that whenever this integral is not equal to zero, then the transition is allowed. Okay, so that seems like an interesting statement, and you just have to calculate this integral, and that's it, and then we're done. But of course, in many cases, that is pretty tricky, right? And so we have to use some insights to determine whenever this is zero or not. So that is, of course, good to know under which conditions that happens. And those conditions are known, fortunately for us. So we don't have to compute this thing every time. We can just rely on some general principles that stipulate that this integral is going to be non-zero. Now, when is the integral non-zero? Under these conditions. Under these conditions, we can say that this integral is not zero. It's not zero whenever the change in quantum number L, okay, the change in quantum number L, the L, of course, is the angular momentum quantum number of the electron in the hydrogen atom. If that is plus or minus 1, then the integral is going to be non-zero. But if delta L is not equal to this, so it's not going up or down by one value, then it is going to be zero. Okay, so this is a pretty tough restriction. There's a second restriction here, and that is that delta ML must equal 0 or plus minus 1. So what is the origin of this? What is the origin of this? Can we kind of relate this, because it seems kind of somewhat arbitrary? Well, it's not entirely arbitrary, turns out. First of all, this delta L rule that we just looked at, this one here, is related to the fact that the photon itself has also a spin quantum number. Okay, and the spin quantum number is actually not half. It's not half like that of an electron. It's actually 1. Here it is. So the spin quantum number of the photon equals 1. There's a word for this. The photon is not like an electron. Electron is called a fermion. A fermion has a spin quantum number here of half, so it's a non-integer quantum number. But the photon is a so-called boson. It has an integer quantum number, 1, and that means it's a different kind of particle, right? The photon and the electron have very distinct properties, and one of their differences is that they have different spin quantum numbers. One is a fermion, and a photon is considered a boson. It has dramatic consequences, in fact. that we will touch on a little later. So this spin quantum number, of course, is related to angular momentum. We know that spin is a source of angular momentum. Okay, so if the photon is interacting with the atom, it's going to be annihilated. It's going to be destroyed. That means you are destroying angular momentum. Well, there is a so-called rule that's called the conservation of angular momentum. You cannot just destroy angular momentum, just it's gone. It has to go somewhere, and it has to go, of course, into the atom. So the electron will take over the angular momentum that the photon had. And it does so by going up or down in angular momentum. That's defined by this L here. So what the photon had in spin angular momentum, the electron is going to take up in terms of orbital angular momentum. And that's why it goes up and down by 1. The second rule here also has to do with another property of the photon. And that's something that I will not spend too much time on because too many details here. But it's related to the so-called helicity of the photon, the helicity of the photon. The helicity of the photon, which is indicated by sigma, is plus minus 1. Okay, that has to do with right-handed and left-handed polarized light. And because of this plus minus 1, this plus minus 1 is there. Okay, so again, it's the same kind of principle as I just stated. The photon has certain properties. It has spin angular momentum. It also has helicity, and these properties must be transferred some way, somehow, to the material, to the electron. And so the electron must take on quantum states that compensate for the change in these spin and helicity quantities. These quantum properties of the photon, some way, somehow, must be preserved, must go somewhere, and the electron takes them on. Okay, so this is the origin, the physical origin of these so-called selection rules. Selection rules that say that if this is fulfilled, the integral above is going to be non-zero, and therefore the transition is allowed. So, long story short, here you see a couple of states of the electron in the hydrogen atom. And you can see now there's more states, and I also took care of the spin-orbit coupling of these states. Okay, so these two states here, this guy and that guy, are the ones we just focused on for a while. So the so-called p state, the term symbols with the p states, 3/2 and 1/2. But there's more. Okay, there's also the s state. So this is the term symbol for the 2s. This is the term symbol for the 3s. And then there are d states. There's 2 indicated here, as you can see, right? So these are all term symbols. Depending on where the electron sits, I can determine the term symbols of the states that the electron can accommodate. And now I'm going to see when can I make a transition between these states. Well, the main rule here is delta L equals plus or minus 1. Okay, and that means if I am in a 1s state, I cannot go to a 2s state. This is not allowed. Okay, because if I do that, then delta L is going to be 0, and that is not allowed. At least it's allowed, but it's not allowed for a photon transition because it must have plus or minus 1. So you cannot drive an electron that sits in the ground state to the 2s1 state with the help of light. That doesn't work. But you can kick it to the p states, either a 3p state or a 2p state with their spin orbit coupled splittings. Or you can go from a d state to a p state and vice versa, or from a p state to an s state. That is allowed because in all of those cases, the delta L is plus or minus 1. Okay, so you see, not every transition is allowed. They are restricted by these selection rules. Okay, so let me now say something about the fact that these splitting energies, the spin orbit coupling energies, are very little in the case of hydrogen, but we already noticed that they can be quite substantial for other elements. And that is because, again, of this z to the power 4 dependence. Okay, so let's focus on this element here, neodymium. Neodymium is, I would not say that it is the heaviest element, but it's a pretty heavy element compared to hydrogen. It's a rare earth metal, right? So this element has actually substantial spin orbit coupling energies, and that is given in the diagram over here. These are just a couple of transitions between states. Now, notice a couple of things. The numbers here are kind of mind-boggling. You see here the term symbol is an I, okay? That is a very high letter in the alphabetic order, and that means that the orbital angular momentum, which is what this term symbol I stands for, is very high, okay? That means a couple of things. It means the states that the electrons will be in are high. They're not just in 1s or 2s. They can be in different states. In this case, they are in F orbital states, because this is a lanthanide element. The electrons in the open shell are in the F states. Okay, so that gives very high total orbital angular momentum. That's why there is an I here. This 4 here is a spin multiplicity. Remember, 2s plus 1 is what this 4 means. If I subtract 1, I get 3, and then divided by 2, so I have 3, 2. S equals 3 over 2. How can it be? Shouldn't that be half? And the answer is no, because this is not due to one electron. It's due to multiple electrons. And effectively here, I can think of this 3 over 2 as 3 electrons are participating. Okay? 3 electrons are participating in this state. So that is very different from what we've seen for hydrogen. And we will get back to this. We'll get back to this if we talk about helium. But you can see the multiplicity, the spin multiplicity is a higher number now. It's not 2, it's something very different. It's 4. More electrons play a role in defining this state. And then I have something that looks even scarier, 15 over 2. That is J. Okay, so this J indicates how the orbital angular momentum and the spin angular momentum are coupled to one another. One way is that they form a total J of 15 over 2. There's other ones here as well. So all of these guys are all I states, so they all have the same orbital angular momentum and the same multiplicity, so the same number of electrons are defining these states, but they have different J values, different spin orbital coupled energies, okay? And that's given over here. See, all these states here, all these split states have different values. These values are significant. The energy differences here are quite large, okay? You see here the transition energies. This is 946. This is 1064 nanometers, 1123 nanometers. These are all wavelengths that are of significance. So we can observe that very easily on a spectrometer. There's splitting in energy that lead to substantial wavelength shifts. So this is not something we can brush under the carpet. We can easily see it with regular spectrometers, and therefore spin-orbit coupling is really defining the spectroscopy of an element like neodymium. Now, why do I bring up neodymium? Is that an arbitrary element? The answer is no, it's actually very important, and that is shown over here. Okay, if you take a green laser pointer, the transitions that you will see in the green laser pointer all rely on the following transition here. This transition, okay? This transition of 1064, that is a transition between this term symbol of neodymium and this term symbol. So that is a transition, the emission from F4, 3 over 2, to I4, 11 over 2, these two term symbols, that transition is what drives your green laser pointer. Okay, so let's look at that, how that works. The green laser pointer is just absolute magic, folks. Very quickly, I'll tell you what's inside this beautiful piece of technology. Most of it, what is inside, are 2 batteries. Takes up almost all the space. There's a piece of electronics right there. And then the magic really happens over here in this little unit. And that's blown up here below. The heart and soul is this little tiny area right here. That is a diode laser. Produces 808 nanometer radiation. It's a little chip. Okay, it produces radiation of 808 that is focused by a plastic lens, and then it's sent onto a crystal. This is basically a glassy material. It's an yttrium kind of material. Okay, it's actually yttrium and then vanadate, yttrium vanadate material, which is just clear glass. That's what it looks like. And then there's neodymium atoms in there. So it's doped. It's a doped glass with neodymium. The same neodymium, of course, we just talked about. The neodymium is absorbing 808, and it's emitting 1064, 1064 nanometer radiation. And that radiation then is going into a second crystal, which is potassium triphosphate crystal. And that crystal is doing, it is so-called doubling the frequency of the radiation. And that means effectively that you halve the wavelength. So you go from 1064 to 532, and the 532 is the green light that comes out, okay? The green light that comes out is 532. That's so-called frequency doubled 1064 radiation from the neodymium ions in the glass. The exact same transition we just talked about, that was 1064 transition, that is what causes the green light from your laser pointer. So it's a beautiful piece of technology. It's some wonderful, interesting optical interactions. It's not simple, actually. There's even some nonlinear optics in here because this frequency doubling is a nonlinear optical effect. So a lot can be said about the laser pointer, which seems like an arbitrary little piece of equipment. It's based on some beautiful physical principles. If you want to know more about this, I'll be happy to chat. This is not part of the exam. I just want to relate this to some day-to-day experiences that you may have. You may not think about the spin-orbit coupling effects as being significant in your life, but in fact, they determine the operation of your laser pointer. Okay, so just to finish off this lecture, I'm going to make a very quick start, just one slide, with something we have to talk about on Friday, and that is the transition from one electron in the hydrogen atom to more electrons, because every other atom in the periodic table has more than one electron. Okay, so in the case of hydrogen, we solved the Schrödinger equation. Here it is once again. Remember, this mu is the reduced mass. Of course, this del squared is the kinetic energy operator. And then this is the potential energy term. Okay, we solved this problem and we found the wave functions. These were the hydrogen wave functions that have 3 quantum numbers, n, l, and ml. Now, what happens if we are making the system more complicated? Okay, and there's a couple of major differences here. First of all, the nucleus is larger, it has more charges, but we can still just simply assume that the nucleus is one particle simply with a higher charge, a higher positive charge. The main difference is that instead of having one electron, I now have 2 electrons to take care of, and that complicates the Hamiltonian quite a bit. So here's the Hamiltonian of helium. It looks a lot longer, okay? Why is it longer? Well, first of all, there are a couple of extra terms in here. Let me start all the way on the right. This term right here is the electron-electron interaction, okay? So you see here R12, that is the distance between these 2 electrons. Distance between these 2 electrons is R12, okay? And so depending on this distance, of course, they will have a Coulombic repulsion. They have the same charge, okay? There's a plus charge here, a plus meaning that they will repel one another. So that is one effect that I did not have in the hydrogen atom. I did not have the interaction between the electron and another electron. So this is an important difference. Then I have basically 2 individual Hamiltonian contributions, one from the first electron and one from the second electron. Each electron will have a kinetic energy term. That is the first term in each of the orange boxes. And it will have an attractive energy term due to the potential energy, okay? That is this term right here. That's the potential energy with the electron and the nucleus. So I have H1, that is the kinetic energy and potential energy of electron 1 with the nucleus. Then I have the same for electron number 2. I can call that H2. And then I have an extra term, which I call V12. That is the repulsive energy, the electron-electron interaction that I did not have in my hydrogen atom. So the problem is, to solve this Hamiltonian, the main problem is the presence of this V12, this electron-electron interaction. If the electron-electron interaction wouldn't be there, it turns out it's not so hard to solve the problem. Okay, so let's first pretend that the electron-electron interaction is simply not there. Okay, So then I only have H1 and H2. So that's basically written over here. So the Hamiltonian in the case, I can just forget about electron-electron interactions. It's just H1 plus H2. This is not such a hard problem to solve, it turns out, mathematically, because if I just take the wave function that I found in my hydrogen problem, I call that basically little psi of the first electron, and I multiply that by the exact same function for electron number 2. Okay, this is also a hydrogen type function. Okay, so this is a hydrogen type function that I solved previously. This one is as well. They don't have to be in exact same state, but they are both just the same hydrogen atom wave functions that I had before. The same form, except for Z, that is the nuclear charge, which now is 2, but everything else is the same. Okay, so if I substitute this one and put it in the Schrödinger equation, it turns out I get a beautiful solution, right? This is called the orbital approximation. I get a beautiful solution because the wave function 1 and the wave function 2 have nothing to do with one another. They are individual solutions of the Schrödinger equation, and therefore, since the Schrödinger equation is just the sum of the two contributions, the energy that you will find is simply the energy of the first particle times the energy plus the energy of the second particle. That is the orbital approximation. So just to make a long story short, I can say that I have two wave functions, okay? Two wave functions for the first particle 1, for the second particle 1. Both of them are just as before hydrogen type wave functions, of which I have the solutions. The only thing that's changing is the value for Z, which now equals 2 instead of 1, but everything else is the same for helium. Okay? The wave function is simply the product of the two wave functions, and the energy is the sum of the energy of the two wave functions. This is a direct consequence of the fact that these two electron wave functions have nothing to do with one another. They are acting independently. Okay, so basically I can simply calculate then what the energy is of having two electrons in this system. It's simply the energy 1 and energy 2 if they are both in the ground state, in the 1s state, so 1s2, 2 electrons in the 1s state, then it's simply, this is the Z again, so that's why there's a 4. This is n squared. Just add up these two energies and I find the total energy of my system. Now, all of this, of course, is done with the notion that we have completely ignored the electron-electron interaction. We just said that these are two independent solutions, but in fact, they are clearly not, because these electrons can interact, and as soon as they interact, they are no longer independent. Okay, so one way to kind of correct for this is to basically look at this integral of this operator here. Okay, so I sandwich the operator V12. This is the repulsive interaction between the two electrons, the electron-electron interaction. I sandwich it between my wave function. Okay, then this is the wave function that I found. And I say, what is this integral? This integral must give me some sort of an idea of what the overall contribution is of the electron-electron interaction. This is an approximate description, okay, and we'll get down to this, exactly why this is approximate. This is not exact, okay, because I am assuming a certain shape of the wave function here. This shape is an unperturbed wave function. It doesn't include this V, okay, and now I'm saying, well, since I have this one right now, let's just calculate this expectation value based on these functions. Okay, so that's an approximation, but this approximation will give us some sort of an idea of the magnitude of this electron-electron interaction. Okay, so, and this is the result. If I take E naught, which is basically the energy I just computed up here, okay, this energy, you know what Hc is times RH. You can just compute this, and if you do that, you find minus HCRH. That is the energy, the unperturbed energy, if the electrons would not interact. Well, they do interact, and that's why I'm adding this correction term, J. Okay, this is not a correct description or an exact description, but an approximate, but it gives me a pretty good idea of how big this electron interaction is. So this is minus 8, so there's a negative sign here, Okay, and there's a positive sign for this 2.5. That means repulsive, not attractive. Okay, so this correction is actually very big. Okay, it's more than 25%. So this is not something we can brush under the carpet. It's a real effect. So effectively, I find minus 5.5 Hc times RH. That is the approximate energy of the ground state of helium based on this description, which is now an approximation. It's no longer exact. The hydrogen functions were exact, but our description right now here is clearly an approximation. However, it's a pretty good one. It's not too far from the experimental values, and that's why we will continue in this vein on Friday. So that's all, folks. It's a lot of stuff to think about already.